All right, so that was our first quiz of the semester. There are only two more. Your next assignment is due a week from today. I'll give you the handout at the end of our class today. Both of the problems that are on that assignment are covering the material that we're doing in class today. And so you should have plenty of time, I hope, to work on that assignment. What we're going to be talking about is called the Nodal Method, and it's a way of keeping track of energy losses through pipelines. And until now, what we've been discussing is just simple situations where there's one pipe. We sort of scratched the surface at complexity when we were discussing the three reservoirs problem and looking at the uncertainty that that can cause. But the new situation today has to deal with when flow reaches a point of divergence where it can go more than one direction. So we're going to look at the nodal method today. Any announcements, questions before we get into it? Yes? So you're asking about the non-circular conduits? Can you say your question again? So the other form of the Reynolds number? It's just depending on whether you know the kinematic viscosity of the water or the absolute viscosity of the water and the density. Yeah, because remember that kinematic viscosity of water is the absolute viscosity of water divided by the density of water. So they're essentially interchangeable. Okay, well let's think back to the Moody diagram. And there's a section of this Moody diagram where things aren't happening very much, where it gets a little bit boring. Now how could a diagram like this be boring, right? But this flat part's a little bit boring because the F values aren't changing. Look at how level that is. I mean, that's not interesting at all. All you have to do is go with the Reynolds number, find the curve, and then it's straight over. It doesn't really require any judgment whatsoever. So what's like the physical interpretation of this zone where the F values are flat? What does that mean? What does it mean about the velocity of water in the pipe? If we're going to like fill in the blank, I would say the velocity of the water in the pipe blank the F value. So in that region it doesn't change. Like the Reynolds number, once you get to a certain point, a certain threshold, any additional velocity isn't changing the F value. So let's say that the Reynolds number is 10 to the 6th. If we go up here to some relative roughness like 0.01, 10 to the 6th gives us the same F value for that relative roughness as 10 to the 7th. It's the same F value. 10 to the 8th, the same F value. So it means that once the velocity is pretty high, once the flow is turbulent, any additional turbulence or any additional velocity is not going to have an effect on the F value. So we call that fully turbulent, when there's a threshold beyond which any additional turbulence does not affect the F value. So this is one of our shortcuts sometimes when we're in those positions that we have to guess an F value. And you've seen some of those situations already, like with the three reservoirs problem, where we don't know what the velocity through the pipe is, and so we can't guess what the roughness might be. Well, one of our moves is just to say, well, as a starting point, let's assume that the flow is fully turbulent, meaning to the right of that dashed line. And we're saying, we'll assume it's fully turbulent, and later on we'll check to see if that's true, but I mean, that assumption is going to give us a better guess than just picking some midpoint, or certainly better than picking some extreme within the range. So from a calculation standpoint, if we move away from the Moody diagram to the Jane equation, for instance, so look in the Jane equation. We've got two terms inside of that logarithm. We've got one term that has to deal with relative roughness. Remember where K sub S means it's a material property. Sometimes we've been calling it epsilon. So the ratio of the material roughness to the pipe diameter is one of those two terms. And the other is having to do with the Reynolds number. Okay, so I said when you start having really high flow velocity, that any additional flow velocity doesn't have an effect on the F value. So think from a numerical standpoint. High Reynolds number is going to make the second term essentially close to 0. So as Reynolds number keeps getting bigger and bigger and bigger, this second term becomes insignificant relative to the first. Was there a question? Well, you can convert to meters, but the units have to be the same on K sub S and D. It's a ratio. So if you're going to say your D in meters, then your K sub S should be in meters, and vice versa. It'll be the same as long as you use the same units for both D and K sub S. All right. So the main thing is high velocities means that fully turbulent simplifies the Jane equation. If flow is fully turbulent, then F only depends on the relative roughness. It doesn't depend anymore on the Reynolds number. So that makes things a little bit easier. Even the Colebrook equation starts looking pretty good when we eliminate this second term because it's no longer implicit. Remember, the implicit equation was that there's F values on both sides, and Colebrook's particularly nasty because it's buried under a radical, it's buried at the denominator, inside a logarithm. All that nonsense goes away when we've got the fully turbulent flow assumption. Now, is flow always fully turbulent? Of course not. There's plenty of conditions where flow isn't fully turbulent. But if we use it as a starting point and then verify, we can adjust later on when we do know the velocity. And so it's always fine as a first guess. All right. So keep that in mind, that that's one of our tools in the toolbox that we're sometimes going to apply. Another one of our tools goes back to fluid mechanics, and it's the continuity principle. The continuity equation was flow in equals flow out. And we spent a whole chapter on that, if you can believe it. So here, consider two pipes that are coming into a junction. Flow X and Y equals flow Z. So at this node, the flow in and the flow out are equal. There's no reservoir at this node. There's no tank. There's no capacity for storage. It's just what goes into the junction has to come out. So we'll sometimes do a control volume around a junction and keep track of these balances. Now the application here in pipe networks is sometimes we face situations where we've got water coming through a pipe and we know how much flow there is, but then it splits. And some of the flow is going through the upper pipe, some is going through the lower pipe. This is a top view, so when I say upper and lower, it really doesn't have anything to do with gravity. The top view here. The question marks are just illustrating that we don't know how much is going through each of those pipes, but what we do know, when they come back together again, assuming that there haven't been any withdrawals in between, that the junction here, the downstream junction, that those two pipes come together and that all that flow is still there. So we could do a mass balance at this junction, and we can say that flow B is just that A, which we knew, minus the C that we don't know. We can write the flow rates in each of those two unknown pipes in terms of the other pipe, which is unknown. And the whole reason for this is we're going to try and set up systems of equations where we have two equations and two unknowns. And this is going to be one of our equations, the continuity equation, where we're going to remind ourselves that I may not know the flow through both of those pipes, the upper and the lower, but what I do know is that flow coming in equals the flow going out. All right. Any questions so far? This is one of the big governing ideas, and so we really have to believe it because we're going to be applying it a lot. All right. I don't see any doubt. So here's an application of that. Let's say, for instance, that of these two pipes, pipe B and C, what if they have the same length and the same pipe diameter and they're made out of the same pipe material? So how would the flow through B compare to the flow through A? Is one going to be more than the other? Why not? Because they're the same. There would be no reason for flow to preferentially go through pipe B compared to pipe C. So the flow would equally split between those two. There's no reason why it wouldn't. Okay, so with that, yeah, go ahead.
How does geometry affect it? Like, they obviously, if they're using the same exact pipe,
Yeah.
geometry of pipes.
Right, so you're saying, oh, this has a little bit more of a sag, something like that. So let's say that there were some local losses here. Like this curve looks a little bit more abrupt, right? So what if this had more local loss? So what do you think would happen in a situation like that where the top pipe doesn't have extreme changes in direction? So in a situation like that, what would you suspect? Where the bottom pipe does have more jagged turns. So which you're right, which pipe, the top pipe would have more flow. Exactly right, good. So along those same that same thinking, what if they have the same diameter and same length, but then pipe B, that upper one, is more rough? Pipe C is going to get more of the flow. It's not going to have all of the flow. So how do you think the water, now I'm going to do a bad thing, the water isn't a person. But how does the water decide which pipe to go through? Years of experience, flipping a coin. College degree, no, the water doesn't have any of those things. So let's say that the water isn't really deciding, but I mean, what does the flow depend on? Some is going to go through the top, some is going to go through the bottom. Like, what's the equilibrium there? In has to equal out, that's true, but in would still equal out if 1 liter per second went through the top and 999 liters per second went through the bottom. Even if it was just a slight difference in roughness, it wouldn't be that extreme a difference, right? So any initial thoughts at what determines the fraction of how much flow goes through one pipe versus another? Yeah. The angle? Indirectly it could, but that's not like the main governing idea. Whoa, he's got it. He's onto something. Okay, go ahead and say it.
The total head loss from, I guess you could say, the junctions.
Okay, the total head loss through the junctions. You're almost there. A little more. The total head loss what? I mean, there has to be like a conclusion of that statement.
Pipes.
Through pipes, okay.
Compared
Compared
to
to the other one.
because the epsilon values would be different.
What did you just say? Different?
Yeah, the epsilon values would be different if one pipe was less.
Okay, the head loss has to be the same through both pipes. Look at it this way. You couldn't have a lot of energy loss through one pipe and a little bit of energy loss through the other pipe because you're ending up at the same location. It's like a road. Think about if you're driving down a mountain and you start at the top of the mountain and you're going to the bottom of the mountain. All right? There's one road that's like straight down, and there's another one that's a winding path. The total elevation change is the same, regardless of which path you take. So that's the analogy. We'll talk about that more in a minute. Let's take a stab at another one of these, though. Okay, what about if the diameter in pipe C is bigger? Now, more flow is going to go through which? C. How come? All right. So, because we've got more area for flow. Very good. If we think about it in terms of head loss, there is going to be less head loss, relatively speaking, through the pipe that has a larger diameter. And so initially, if we were to like change these on the fly, more water would want to start going through this pipe that we enlarged until it came into an equilibrium. And then, although there's more flow rate through this pipe C, the head loss through both would be the same. Now this one, what about this? Which is going to get more flow? This is a logic problem here. All right, let's take a vote. Let's crowdsource this. Okay, which pipe gets more flow? Pipe B. Okay, pipe C. Anybody have an alternate answer? Again, 2 for 2. He's getting the 3-pointers today. Not enough information. Okay, it's indeterminate. So we don't know. Like one of these, okay, pipe B is bigger. That means we're going to have more flow through pipe B. But pipe B is longer, which means that there's more head loss there. And so then that would say C is better. And so it's kind of like a toss-up. And then pipe C is more rough, which makes things ambiguous there. And so we'd need more information. We can't say for sure which is which. Okay, so here's the main underlying principle here, is that regardless of which pipe you go through, the energy loss is the same. So the head loss through pipe B equals the head loss through pipe C. And Darcy-Weisbach equation, we could substitute in all of the terms for the Darcy-Weisbach equation. And so if we know the friction factor for pipe B and the length for pipe B, so we could come up with a ratio of the velocities with this. By substituting in the diameters, the lengths, the roughnesses, then we could get like a ratio of how much flow is going through B relative to how much flow is going through C. And we could use that ratio back here in the continuity equation to find out how much flow goes through each pipe. That's the direction we're headed in. So any questions on this so far? Yes?
Yeah, the last one, you said that since pipe B was longer, there would be more head loss in pipe B than pipe C.
Yeah. So in this, okay, the first one, bigger diameter means B is more flow, right? But longer length means B is less flow. So these first two are kind of canceling each other out, because the pipe that has a longer length is going to have more resistance compared to the pipe that has a shorter length. So and the way to know that is look at what's in the numerator and what's in the denominator of the Darcy-Weisbach equation. Anything that's in the numerator is going to give you more head losses when the number is larger. Does that answer your question? Okay. Okay. So our big ideas so far is continuity equation and energy is equal. I mean, think of it this way. You couldn't have like 100 meters of head at this junction and go through one pipe and end up at 90 meters of head, and then go through the other pipe and end up at 80 meters of head. It has to be, when you get to the junction, they have to have the same amount of energy, regardless of which path you took. Okay? I just said that. It doesn't matter how you get from 1 to 2, the head loss between the 2 points is the same. Can you tell I've given this lecture before? All right. So energy equation is going to look a little weird when I show it to you. I hope you don't feel dizzy or disoriented. When I show you this new version of the energy equation, it's just the same energy equation you've seen before, but here it is. All right, don't flip out, all right? Stay with me. No, okay. Obviously, it's no big deal, right? H, what we mean by H is pressure head plus velocity head plus elevation. That's H, means head, total energy. So we're saying that the total energy at 1, where flow is going from 1 towards 2. All right, so we're starting at 1. The total energy at 1 minus some losses, okay, FL divided by D. Which losses do you think those are? Friction losses. What about the sum of K naught? Local losses. So those are our two loss types. So we're losing some energy between 1 and 2. So that's why the minus. Now, times Q, absolute value of Q, divided by 2G A squared. We've seen something similar to that before. That's just the velocity head. That's the velocity head. And instead of saying v squared divided by 2g, there is an advantage to us sometimes saying q squared divided by 2ga squared. So sometimes it's better for us to write it that way. I'm glad you asked that. Yes, there is. Because sometimes we say q times the absolute value of q, because sometimes q has directionality, like a negative, and we want to preserve that negative sign in the q. And if we had just squared it, then that negative value would have gone away. But if we preserve the directionality, like if we just do q times the absolute value of q, then that would help us to correct when we've made some bad assumption about the direction of flow. That'll come up later on, not immediately, but I'm glad you asked that question. And the same thing for this pump term here, h sub p. Q divided by the absolute value of q, that's just so that if we assumed flow was going one way, but it really turns out flow is going the other, that absolute value term down in the denominator will help to sort it all out. Oh, well, all right. If you want to be picky about it. You can, okay, go ahead. You can write it however you like. Yes, it would. I don't know why. There's no reason. There's no reason why any of this. It's just all made up. All right? Huh? Yeah, what is knowledge? Why are we here? What's the meaning of life? All right. No, that's a good question. I'm not, yeah, all right. Okay, so again, this is just the energy equation, right? So here are all the definitions of the energy equation that we've been talking about. We say that flow is from 1 towards 2. That assumption is built into this version of the energy equation. 1 and 2, that has meaning. Water flows from 1 towards 2. Now, we can use this equation to find out the head at a certain location, and we can use that nodal approach to find out how much flow is going through pipe B compared to pipe C. And so kind of what we would do in a hypothetical problem would we would find out how much head there is at 1 by combining the pressure head, elevation head, and velocity head. We would find out the head at 2 in terms of the flow, the unknown flow rate through each of the pipes. So the Q that's here initially is going to be unknown, QB versus QC. And then we can equate the two using the continuity equation. And then later on, if the problem asks us to find out how much head is there at 2, then it would just be applying that energy equation. You'd start with the head at 1 minus the losses plus the gains if there's a pump. Sometimes there is a pump, sometimes there's not. That's the general form of equations like this, problems. All right, so here is what we're actually going to do to get some experience with the nodal method. We have a network where water is flowing through pipe 1, and we know the flow rate. Well, we know the velocity. In this table, it's telling us that the velocity is 5.287 meters per second as the water goes through that. Oh, we do know the flow rate. It's 3 cubic meters per second. We also are given the head at junction A. Now, all we're going to solve in this example is we want to know how much of the water goes in 2 versus through 3. So we want to find the flow rates through 2 and 3. And so let me give you an overview of the steps you need to follow to solve this. Just to save some computational time, I've already provided the cross-sectional areas of the pipes. From the table, you can find the lengths and diameters. The epsilon here, since it's galvanized iron, we're going to use 0.15 millimeters. All right. Equating the two energy losses here is how we're going to find the ratio of the velocities, but the F values are unknown. So you're going to invoke the fully turbulent flow assumption. Now here's a really important thing. Anytime you use that assumption, you have to check to make sure it's valid. You can't use it unless you check later on. So keep that in your mind, that after you find the flow rates, you're going to use the Reynolds number and the full version of the Jane equation just to make sure that F value you calculated using the fully turbulent flow assumption is within 1%. And we'll say that a 1% difference is our threshold for needing a whole new step of recalculating everything based on an updated F value versus just saying it's good enough. All right, so calculate your fully turbulent flow F values, calculate the ratio of the velocities, use the continuity equation to find out what's the flow through 2 versus the flow through 3. The total flow is 3 cubic meters per second. I want you to calculate how much of that 3 goes through each of the pipes. Okay, I'm going to be circulating around with my copy of the solution, and if you've got questions along the way, I'll be happy to answer those, and then we'll, after several minutes, take a look at the solution here on the screen. All right, so everybody knew to start off with the fully turbulent flow assumption, right? So we can just slash and burn the Jane equation, simplify it. We don't have to bother with the Reynolds number term at all, just putting in the relative roughness term into the Jane equation. So we get our 2 F values for each of the pipes. And then saying that the energy loss is equal through both routes is where this comes from. The idea that the head loss through pipe 2 is equal to the head loss through pipe 3, which has to be the case because they meet back together again. And so we can rearrange in terms of either V2 or V3. And it doesn't matter which one you solve for. We're just looking for some factor that expresses the ratio of V2 and V3, because it's that ratio that we'll substitute into the continuity equation. Okay, so I did that. All right, I see lots of smiles of delight, meaning that people did it correctly. Any questions? I'll give you a few minutes to copy that down if you are still working on it. All right, so one thing I did here is I wanted to make sure that Q2 plus Q3 equals the 3 cubic meters per second. So you double check the sum of those two flows, and it's pretty close to 3, so that's a good sign. And then we need to check the validity of the fully turbulent. I don't know why my solution is smeared. I think it's haunted. I know what you did last summer. All right. So we calculate a new Reynolds number for each of the pipes, and then we put that into the full version of the Jane equation and get our new and improved F values. And it turns out that that's less than 1% different than what we had when we used the fully turbulent assumption. So, you know, for pipe 2, the F value there was 0.01493 instead of 0.1498. So we're golden there, and things are also looking good for the other one because it was 0.01567. So it changes very little. So there's no need to do this all over again with these updated F values. But let's say that fully turbulent flow assumption wasn't valid, you know, within the 1%, then we would just take these F values and drop them back into this step. So we could still use all the algebra that we've done previously, but we just put in a different ratio of F values into that to find the different ratio of V2 and V3. It probably wouldn't change a lot. It would change a little, but that's the example. on how to find the flow rates. But problems like this sometimes ask, how do you find the pressure at D? See this drawing here? It's saying if we gave you the pressure at A, what's the pressure at D? And we're not going to do all those calculations in our remaining 11 minutes, but I'll explain it to you. Okay, the pressure at A is how we find the head at A. Let's assume that all the velocity, that the elevations are constant. And so the Z terms at each of these junctions is equal. So the total head at A would then be the pressure head and the velocity head. And we could get the velocity head because we know the velocity at junction A, and we know the velocity at junction B. Just for simplicity, we could say it's the same as the flow through pipe 1. So we could find the energy at A, we could find the energy at B, and then we have losses through either of the pipes using the energy equation. So we could find the head at junction C. So that would say H2 would be H at C, the downstream junction, because flow always goes from 1 towards 2. So we'd have some total head at B, and we could find the head at C by this equation. There's no pump, so that term cancels out. We would find, using the flow rate that we know through pipe 2, how much losses there are. And then that would allow us to find the total head at C. The same idea through pipe 4. We would find the losses through the pipe and find the total head at D. And so that once we know the head at D, we can find the pressure, because remember the definition of the total head is it's the elevation head, the pressure head, and the velocity head. And so if we have the total head at D, then that would be the pressure head at D plus the velocity head at D and the elevation at D. And so assuming, like I mentioned earlier, that all of the elevations are the same, we would substitute in the known velocity through pipe 4 to give us the velocity head. The head at D is known just because we started upstream and we're decreasing our energy through each pipe segment. And so this pressure at D would be the only unknown that we'd need to solve for. So that would be our procedure. And it takes a lot of extra calculations, and we don't have a lot of available time, so we won't actually do that. But what I do want to do is show you the problem you're going to be solving on the homework that's due a week from today. It's got 3 pipes instead of 2. It's not that much more complicated because the principle remains the same. We're going to be getting from our origin and our destination, there's 3 different routes that you can travel, but you're ending up at the same amount of energy, regardless of which route you go. So you could write an equation that relates the velocity 1 to velocity 2. You can also write an equation that relates velocity 1 to velocity 3, because the head loss through pipe 1 equals the head loss through pipe 2, and that also equals the head loss through pipe 3. So all of the head losses are the same. Now just to make things even more clear, I've put together a little help handout here. All right. So that handout I've just given you, I hope, will make problem 42 on your homework that much easier to solve, because it just kind of step by step tells you what to do. All right. So there's two homework problems in what's due a week from today. One of them is this, the nodal method with 3 pipes. The other one looks like it would maybe not be a nodal method problem, but it is. It is a nodal method problem. So I wanted to save a little bit of time so we could discuss this handout problem together. All right. Okay, so here's the handout problem. There is a reservoir connected to junction A. Ignore the length of the pipe between junction A and the reservoir. The purpose of this reservoir is just to fix how much energy there is at A. Because that reservoir is directly connected to it, we know the head at A is 25 meters. In the same way, we know the head at B is 20 meters. What we're not sure about, though, is how much water is flowing through each of these pipes. So what you're going to need to do is apply the nodal method in 2 different spots. At junction C, what we've got is 0.2 cubic meters per second coming in, and then you have to assume which direction the flow is going, because it could maybe some of it's going from C towards A and some of it's going from C towards B. Maybe that's just what makes most sense to you. What you'd need to do then is you'd need to calculate how much head there is at A in terms of the losses or gains through the pipe. So there's also some tips on this handout explaining, how to think about this problem. I think it's reasonable to use Excel to calculate R values, and we'll talk about what R values are in class next time. But I think this actually isn't a problem that I've ever solved using Excel before. I mean, I'm sure you could, but I think once you get a few parameters calculated with Excel, it maybe makes the most sense to solve it on paper. But the bottom line here is that we're using the nodal method because it's just we have to do it 2 times. There's the upper half of the network and the lower half of the network, and what we know is that at C and D, continuity is honored, and then the energy equation side of things is we know how much head there is at A. But think about the head at C. The head at C has to be correct regardless of whether you got there from A to C or from B to C, because the head is known at both A and B. At A, it's 25 meters, and at B, it's 20 meters. And so what we should be able to say is the head at C is 25 minus some losses, like I'm going to call it R, and you'll learn more about R's next time, R times QAC squared. And then we also know that head at C is 20 plus some R value QBC squared. So 2 equations and 2 unknowns. Your 2 equations are going to be the energy equation and the continuity equation, where continuity tells us that pipe A and C, pipe AC and BC together have to have the flow rate of 0.2 cubic meters per second. But then the energy equation tells us that we kind of know what, on a relative basis, those flow rates are going to be, because we know how much energy there is at A and B. So we'll have time to discuss that in class next time. I won't have any more presentation for it. So what I'd like you to do is start thinking about that problem, try and solve it, take a stab at it. And if you have specific questions, I'll answer them on Thursday. But I won't have any additional tips beyond the lengthy and extensive tips that are on that handout I've already given you. All right, I will post the solution to the homework that you submitted today. That's actually available now, and I'll grade your assignment soon. So thank you. That's it for today. I'll see you Thursday.